everyone, welcome to this definitive exam prep explainer for NCP-MCI 7.5 3.1, Virtual Switches and Open vSwitch. Today, we're going to break down the absolute core of AHV networking for your certification. Look, if you want to pass this exam, and honestly, if you just want to be truly effective in your day-to-day operations, you need to understand not just what these components are, but exactly how they behave when your cluster scales. So we're going to take our time today. We'll go deep into the architecture and give you a steady, deliberate look at the actual mechanics behind cluster networking stability. Here's our blueprint for today. We'll be covering sections 1 through 5, pacing you through the architectural what and the heavily tested why behind it all. All right, let's jump right in. Section 1. Why virtual switches matter. Okay, we've got to start by defining our first crucial acronym, Open vSwitch, or OVS. At its foundational level, OVS is an open-source software switch. But here is the critical part you need to remember for the exam. It's implemented directly in the Linux kernel. Now, why does that kernel implementation actually matter? Well, it means it operates with incredibly low latency and super high throughput efficiency. OVS runs automatically as a service on every single AHV node. You can kind of think of it as a localized Layer 2 learning switch that maintains its own MAC address table right there on the host. Its main job on that specific host is to act as the traffic hub, connecting the controller VM, the CDM, the hypervisor itself, and your guest VMs to each other and the physical network. But keep in mind, at this stage, OVS is highly localized to just that individual host. Now zoom out with me from that single host to the whole cluster. This is where a virtual switch, or VS, comes into play. A virtual switch is a logical construct. It defines a collection of AHV compute nodes and their uplink ports. Crucially, it's a logical aggregation of the exact same OVS bridge across all those compute nodes in a cluster. It's not just sitting on one host. I like to think of a virtual switch as a giant, invisible, physical chassis switch that spans your entire data center rack, except it's implemented purely in software. It logically spans your entire Nutanix cluster, which is awesome because it allows your VMs to experience a single unified network topology no matter which physical node they actually sit on. Moving right along, Section 2, Anatomy of a Virtual Switch. You're going to want to write this formula down for the exam. Configuring a virtual switch means you're configuring a combination of 3 specific things: bridges, bonds, and VLANs. Let's break down the role of each one. The bridges act as the actual virtual switch instance that actively manages the traffic flow. The bonds, they provide NIC teaming. They aggregate the physical network interfaces on the AHV host to make sure you have redundancy if a cable gets pulled, plus aggregated bandwidth for your heavier workloads. And finally, the VLANs. These are used to segment that virtual network, making sure your management traffic stays totally isolated from your guest VM traffic, keeping everything secure and organized. Now, the primary real-world example of this formula in action is VS0. This is the default virtual switch, and it's created automatically during your AOS and AHV installation. Literally, the moment an admin finishes installing the software and the cluster spins up, VS0 is already there, ready to go, serving as the foundational networking bridge connecting the default bridge on all your hosts. Because VS0 is so incredibly foundational, the certification exam focuses heavily on its specific characteristics. And the test writers, they will absolutely try to trick you here. For example, they might give you a scenario where an admin attempts to clean up the network by deleting VS0. You need to confidently know that it fundamentally cannot be deleted, period. Furthermore, you gotta know that it maps to and aggregates the default bridge, which is named BR0, across all nodes. Also, it's never empty. It always has at least one uplink configured so you don't accidentally isolate the host. And finally, right out of the box, it defaults to the active backup uplink bond type. Which brings us to Section 3, Real-World Bond Mode Examples. Let's actually look at the math and the mechanics of the 2 most common configurations you're going to be tested on. Our first example is active backup mode. Remember, this is the recommended default setting. It safely transmits all traffic over a single active adapter at a time. What does that mean in practice? Well, if your host has 2 10-gigabit NICs, your maximum host throughput at any given moment is exactly 10 gigabits, with the second NIC just sitting in standby waiting for a failure. Contrasted against this is the active-active mode known as balance-tcp. Now, this requires Link Aggregation Control Protocol, or LACP, to be configured. It actively balances VM NIC, TCP, and UDP sessions among your adapters. This cranks up your bandwidth utilization well beyond a single adapter, pooling those resources to give you a maximum theoretical host throughput of up to 20 gigabits. So the underlying why for choosing balanced TCP is pretty obvious, right? Maximizing bandwidth utilization across multiple physical NICs. But listen, this is a serious operational configuration. It absolutely requires configuration on your physical top-of-rack switches. By the way, the default LACP speed in AHV is set to fast. That means a 1-second heartbeat. Now, pay close attention to this operational warning. If you ever need to disable LACP and revert to active backup, you must ensure you also turn off LACP on the connected top-of-rack switch port. Why? Because if the physical switch is still expecting those LACP negotiation frames and the host just stops sending them, the switch will automatically suspend the port. That blocks your bond uplinks entirely and causes a massive network outage for that host. Definitely not a good day at the office. Let's pivot now to Section 4, Common Exam Traps. I want you to imagine this exam scenario. You're migrating a highly critical VM from node A to node B during a late-night maintenance window. The VM successfully moves to the new host, but suddenly, it completely drops off the network. Total loss of connectivity. What is the most likely architectural violation here? Take a second to really think about that. Right there in the AHV administration guide, there is a strict, non-negotiable rule. The mixing of bond modes across AHV hosts in the exact same cluster is not recommended, and frankly, it is not supported. So here's how this inconsistency builds a massive problem in your cluster. Let's say host A is perfectly happy using the default active backup bond mode, but an eager admin went in and configured host B to use the LACP balance-tcp bond mode, thinking they were doing a good thing and improving performance. Because those hosts now have fundamentally different network behaviors, your overarching virtual switch is officially in an inconsistent state. The underlying reason this trap appears on the test is because of what we defined earlier. A virtual switch is a logical aggregation across the entire cluster. It has to be perfectly consistent. Think back to our giant physical chassis switch analogy. If the bonds don't match exactly on every node, or if a virtual switch is entirely missing from one host, that logical aggregation just completely shatters. When Prism tries to migrate that VM, it expects the exact same network landscape to exist on the destination host. So when the VM arrives on host B, it literally has nowhere to plug its virtual cables into because the underlying bond architecture is mismatched. The network mapping fails and the VM drops its connection entirely. Prism Central will actually throw a specific alert for an inconsistent virtual switch state if it detects this situation, and you're going to have to resolve it before migrations will succeed again.
Almost at the finish line here. Section 5, Key Facts to Memorize.
Let's wrap up with a rapid-fire review of the absolute non-negotiables you need to lock into your brain for this certification. Feel free to take a screenshot if need to. First, the virtual switch formula. It's composed of bridges, bonds, and VLANs. Second, the default virtual switch is VS0. It aggregates BR0, and remember, it absolutely cannot be deleted. Third, the default bond mode right out of the box is active backup, which safely gives you a max of 10 gigabits of throughput per 10 gig adapter. And finally, the golden rule. A virtual switch must be perfectly consistent across all hosts in the cluster, otherwise your migrations will fundamentally fail. So, I'll leave you with this question. Are your virtual switch configurations perfectly consistent across every single node in your environment? Go check your Prism element today, because understanding why that consistency is the foundation of AHV networking stability isn't just how you pass the NCP-MCI exam, it's how you keep your infrastructure running flawlessly when it matters most. Thanks for joining me on this explainer, and good luck on your certification.